right, in this section we're going to look at another way to find the volume of a solid of revolution. In the last section we saw that if we took a rectangle that was perpendicular to the axis of revolution, we would get either a solid disk if that axis was abutting the region itself, or maybe a washer, like a disk with a hole punched out. And in this section we're going to see how we can also find these volumes by drawing a rectangle that is parallel to the axis of revolution. So in this sort of generic setup that we have, right, so this is our function y equals f of x. That's the curve. And then I'm looking at the region bounded by this curve and the x-axis and the lines x equals a and x equals b. So that's this region. It's a region that we, may have found the area of a couple sections ago. And now we're going to find the volume. Now we're going to revolve this about the y-axis, right? So here's our axis of revolution. In the last section we would have drawn, we would have modeled this and tried to do this by drawing horizontal rectangles. And that, if you look at this particular region, you probably see that would actually take a couple of that would have taken a couple of integrals and also resulted in a disk, because we'd have like this big hole right in between that would give us a washer. So what we're going to do now is draw this rectangle that is parallel. And what's really nice about being able to do this with a vertical rectangle here is that now I can see that one integral will do the job, because as I imagine sliding this rectangle to the left and to the right through the region, it's always the curve y equals f of x on top, always the x-axis on the bottom, so the boundaries don't change. And so for the same reason we would opt for vertical rectangles if we were finding the area, that makes it pretty appealing to be able to use vertical rectangles here. So it's a vertical rectangle, which means it has a delta x width, and the length of this rectangle is just given by y. Now, in general, the length of the rectangle, right, is top minus bottom. It happens to just be y equals f of x here because the bottom boundary is the line x equals 0, is the line y equals 0, which is the x-axis. So now, imagine, this takes a little bit of visualizing. So we're going to take this rectangle, this blue rectangle, and we're going to revolve just this rectangle kind of about the axis of revolution, about the y-axis, right? And when we do that, we get this shell shape. That is mostly hollow. Right? Like there's all this empty space. So what I've got here, I'm pretty bad at drawing shells, as you can see over here on the left. So I kind of borrowed a figure that was done on a computer to draw this. So the darkly shaded part of this figure on the right here, that's the actual shell. And then there's all this empty space in the middle. Now, the thickness of the shell, that is delta x, that's given by the thickness of the rectangle. The height of the shell is given by the length or the height of this rectangle. So the rectangle that I've drawn in blue here, that rectangle is like right here. So this height is y or f of x. And our axis of revolution is right in the middle. So that's the y-axis here. Now the radius. Now when we ended up with disks, the radius of the disk was the length of the rectangle, and that's because that was the distance from the outer edge of the rectangle to the axis of revolution. When we were working with disks, the axis of revolution was sort of abutting the region itself. In this case, the axis of revolution is over here, kind of separated from the rectangle. And a radius is always going to indicate a distance to the axis of revolution. So over here on the left side, if I look at, and I'm going to actually kind of just get rid of the marks I made, the gray marks of the kind of inadequate shell. Over here on the left side, where we see like the original region before we revolve anything, the distance from the axis of revolution out to the rectangle, that's the radius. And in this case, you know, that radius is a horizontal distance. It's a right minus left. And if I imagine that I have drawn this rectangle at some arbitrary x coordinate, then this radius is x minus 0, because the left x coordinate is 0, or just plain old x. So the radius is equal to x here. If you're revolving about the y-axis, your radius is going to be x if you're using shells and revolving about the y-axis. Similarly, you'll see that if we revolve about the x-axis using shells, so we have horizontal rectangles, your radius would be equal to y because it's a top minus bottom expression. So now, what you have here is this shell, and the way that we find the volume of the shell is, imagine you could cut the shell and unfurl it. You know, like it's a hollow shell, just cut it up the side and roll it out, and you will see that it is like a very thin box, right? It's a box that has a width of this, you know, delta x. And so then we just need to find the length and the height, right? And those two dimensions are, you know, the height is y equals f of x, and the other dimension is the circumference of the shell, of the circle that is the base of that shell. And so the circumference is 2 pi r, and so using length times width times height of that like unfurled, you know, rolled out thin box, we get circumference times height times thickness, and that gives us this result down here. So when I think about, you know, there are, you know, if I scroll down, you'll see we have these integral formulas. But when I'm doing a shell problem, you know, if I'm finding the volume of revolution by using shells, the one formula I remember and that I use, and I just sort of try to apply it to the actual figure that I've got, the region that I've got, is that delta V is 2 pi r times height, 2 pi r h times thickness. And of course thickness is either delta x or delta y, depending on the type of rectangle that we have drawn. So let's jump in and do some examples. In example 3.9, we're going to take this region bounded by the graph, the curve they've drawn for us, and the x-axis between 0 and 1 about the y-axis. So, okay, so they've provided us with a graph. We know that if we aren't provided with a graph, the very first thing we need to do is sketch the region, right? We need to know what it looks like in order to see, you know, what we end up with or what kind of rectangles we need to draw. Our axis is the y-axis. So they don't say use the shell method, but if we're going to use the shell method, we have to draw rectangles that are parallel to the axis of revolution. So that means we're going to use vertical rectangles. So here's a sample rectangle. It has a delta x width. The height is the length of that rectangle, top minus bottom, and that is just the function itself, x minus x cubed, because the bottom is y equals 0. And the radius, right minus left, is x minus 0, or x. So this vertical rectangle, when revolved about that axis of revolution, will result in a shell. And the sample shell has a volume of 2 pi RH times thickness, and in this case that thickness is a delta x thickness. Now I'm going to just plug in the dimensions that we have found on the figure. So this is 2 pi x times x minus x cubed times delta x. And knowing that I'm going to end up integrating, you know, I'm setting up an integral here, I'm going to go ahead and distribute the x. So you have x squared minus x to the fourth. So there's our delta V. And just like with areas and just like with using the disk method, if we can write the expression for the volume of the sample shell, then the integral pretty much writes itself. So the volume is 2 pi, of course I'm going to yank that constant factor outside of the integral, times the integral of x squared minus x to the fourth dx, and the only thing we're missing are the limits. The limits of the integral come from the limits or boundaries of the original region. Before we revolve anything about any axis, the actual region is this right here, right, that I'm outlining in red. And so I imagine, since it's a vertical rectangle, we're kind of sliding this rectangle to the left and to the right. The very leftmost value I could pick is 0. The rightmost value I could pick is 1. It doesn't hurt that they actually kind of gave us those boundaries in the problem itself. And now that we have it set up, the hard part is over. Let's evaluate this integral. It's a polynomial, so there's no u substitutions we need to worry about. We're just going to go ahead and use the power rule. So we bring over the 2 pi. Integrating that function, we get 1/3 x cubed minus 1/5 x to the fifth. Our limits are 0 to 1, and now we can plug in our limits. If I plug in 1, I get 1/3 minus 1/5, and subtracting, if I plug in 0, every term has a factor of x, so it zeroes out. Let's see, if I get a common denominator here, that's 5/15 minus 3/15, that's 2/15. 2 pi times 2/15. And that gives us 4 pi over 15. Alright, in this next example, we're going to find the volume of the solid form by revolving the region bounded by the graph of this function, 1 over the square of x squared plus 1. And the x-axis, they give us some bounds. We're only going to look at this region from 0 to 1 about the y-axis. So we need to graph this. I'm going to throw it in my y1. 1 over, I need parentheses here, x squared plus 1, close parentheses, square that. And I'll look at it on the, I guess, the standard window at first, from minus 10 to 10. Alright, so clearly what's going on is close to the origin. So I'm going to do a zoom box, and maybe I'll go from minus 1.5 to 1.5. And I know the function is only positive because the numerator and denominator have to be positive. So I'll go from 0 to, let's say, 1.5. Let's see what it looks like now. All right. So the graph looks kind of like this. Now, they said only look at this region bounded by this curve and the x-axis from 0 to 1. So our region basically looks like this. We're revolving at about the y-axis, so if we're going to get a shell, we're going to have to use vertical rectangles. It has to be parallel to the axis of revolution. So here's our sample rectangle. Which has a delta x width. The height of the shell is the length of that rectangle. And that's going to be just the function 1 over the square of x squared plus 1. Now, when we revolve this rectangle about the y-axis, right, we could see that the solid itself is going to exist over on the left side, right, because, you know, we're revolving it. It's going to go 360 degrees around. And sometimes people get confused about what the limits ought to be, and so I'm just going to repeat myself from what I said in the last example. The limits of your integral are always going to be obtained from the original region. You know, before you revolve anything, about any axis, you are going to take a look at this region. You're going to imagine, since it's vertical rectangles, that you could sort of slide this rectangle to the left and to the right. And so our limits are going to be from 0 to 1. Now our sample shell, again, the only formula I memorize for shells is 2 pi RH times thickness. 2 pi RH, and thickness is again delta x because it's a vertical rectangle. Our radius, again, here is, oops, let me use a different color there. Our radius is again x. We imagine, right, that we've drawn this rectangle at some arbitrary x coordinate. And so the distance from that rectangle to the y-axis is x. And so this becomes 2 pi x times the height, which is 1 over the square of x squared plus 1 times delta x. Now, there's our sample shell. Let's set up the integral. Going to take the factor of 2 pi outside the integral. Integrating this, I've got this fraction x over x squared plus 1 squared dx, and our limits are from 0 to 1. So this one is not a polynomial, right? I think we're going to need to make some kind of u substitution, and maybe give it some thought. Pause the video a bit if you want to kind of guess or do a little side work, kind of see where this is going. But based on that factor of x in the numerator, I'm going to say let's let u equal x squared plus 1. So then du is 2x dx. I need a factor of 2. And I'm going to compensate for that by dividing by 2 outside. Now this becomes, let's see, the 2's out there cancel, so we have pi times the integral from 0 to 1. Now if I think about how I'm going to integrate this, I end up with du over u squared. It's not du over u. U is being squared in the bottom, so I'm going to rewrite that. That's u to the minus 2 du. This is a power rule integral, not a log form. So integrating, we get, let's see, u to the minus 1 over minus 1. That's a negative 1 over u, using the power rule from okay, I'm going to pause here for a second. I just did something kind of in poor form. I rewrote it with u's, and I just brought down my limits as they are. This is something we want to avoid. These are x limits up here, right? And it's understood they're x limits because we're integrating with respect to x up here on this line. When I bring them down here, I need to state explicitly that these are still x limits. So x equals 0, x equals 1. I don't want to think that I can plug in 0 and 1 for u, because I can't. Now, we have a couple of options. We could rewrite the expression -1 over u with our x's and then plug in 0 and 1, or, and a lot of people do this because they find it convenient, you can just find your u limits. So, for example, when x is equal to 0, u is equal to 0 squared plus 1, or 1, and when x is equal to 1, u is equal to 1 squared plus 1, or 2. And then that translates our limits from x equals 0 to x equals 1 to the limits 1 to 2. So now if we plug in these u limits, I get minus 1 over 2 minus, if I plug in 1, you just get -1, so minus a -1. Let's see, -1/2 plus 1 is 1/2. So we get pi over 2 for our volume. All right, we're going to do one more. This one will take a little bit of doing because we're going to model it and then we're going to do the integral. We're going to find the volume in a couple of different ways. So we have both a disk method and a shell method for finding the volume of a solid of revolution. And you might ask why we need two techniques. Couldn't we use, disks and washers for everything, or couldn't we use shells for everything? And by and large, it's probably possible to set up an integral either way, right? It really just boils down to what integral do you end up evaluating? How much work to set up the integral, I guess, and also the integral that you end up with, is it something we know how to integrate? We don't know how to integrate everything, right? I mean, integration is a tricky process. So it's possible that setting it up one way could yield an integral that's easy to do, and setting it up the other way would require a lot more work. Or it's possible that setting it up one way will give us an integral we don't know how to do yet. So we really want to, it's good to have both of these methods so that if we hit a brick wall trying to find a volume in one technique, we have another thing we can try. So in this example, they want us to use both the shell and the disk method to set up an integral that will give the volume of a solid formed by revolving the region bounded by the graph of this function y equals 1 minus x squared over 16. Let's see, bounded by that graph, between -4 and 4, about the x-axis. Okay, so first let's sketch this region. So 1 minus x squared over 16. And they tell us that we only need to look at this from -4 to 4. I'm going to give a little bit of wiggle room on either side of that window, so I'll go from, say, -5 to 5. Now, 1 minus x squared over 16 between -4 and 4 is entirely positive, so I only need the y min to be 0, and the maximum value on that window is 1, because we're taking 1 and then we're subtracting something positive from it as I move away from x equals 0. So I'll have a y max of 1.5 there, and we'll see what it looks like. Okay, so it looks something like that. Now the scale, actually, maybe I'll adjust the scale because this looks, I think the actual shape of the region will be slightly skewed by the uneven scale. So I'm going to make my window, maybe I'll let y go up to like 8 or something. Let's see what that looks like. Yeah, okay. So it is a little bit more shallow. I'm going to just try to get a nice sort of picture of this. It doesn't have to be perfect. 1, 2, 3, 4. I could tell that when, we could use the graph to help us out. Let me try to make that a little bit more even. We could tell, we could either use the graph on the calculator to help us out with this, but algebraically, if you just sort of analyze this, the function itself, I could tell that y is 0 when x is 4. Looks something like this, all right? So now, let's see. It says use both the shell and disk method to set up an integral. And we're revolving about the x-axis. So look, the solid is well defined, right? They gave us the region, and they tell us what axis to revolve about. So here's what that region looks like. And we're revolving about the x-axis. So it'll look maybe kind of football-shaped or something like that, maybe a little bit more pointy on either end. But now with disks, our sample disk, think about what kind of rectangle we'd have to draw to end up with a disk. We're revolving about a horizontal axis. With disks, your rectangles have to be perpendicular. So with a disk, we'd have to draw a vertical rectangle. It would have a delta x width, and the radius of the disk is the height of the rectangle, or the length of the rectangle. And in this case, that's just the function 1 minus x squared over 16. So our sample disk has a volume of pi r squared h. With disks, the height of the disk is the delta x, is your width. So this is pi times 1 minus x squared over 16 squared, there's r squared, times delta x. And the limits of this, well, I imagine sliding this rectangle through the region to the left and to the right, and so we would integrate from minus 4 to 4. So the volume will be given by pi times the integral from minus 4 to 4, 1 minus x squared over 16 dx. Now, the example just asks us to set up an integral, so we're not going to evaluate this. Hold on a second. I gotta remember to bring down that square. But we could evaluate this without too much work. To integrate, expand the product, right? FOIL that out. And then it's a polynomial. So we just need to use the power rule. So there's the disk method integral. Now for shells, if I'm going to end up with a shell, I got to draw a rectangle that is parallel to the axis of revolution. So I'm going to draw this rectangle in green. So it's this big long rectangle. And this rectangle, because it's a horizontal rectangle, has a delta y width. The radius will be the distance from the rectangle to the axis. So in this case, the radius, top minus bottom, is y minus 0, or y. Right? I imagine that I'm drawing that horizontal rectangle at an arbitrary y coordinate. So if I draw this at some y coordinate y, then the radius, that distance, is just y, whatever that y coordinate is. Now, the height of this, this is a parabola, right? 1 minus x squared over 16. It's symmetric about the x-axis, or the y-axis, rather. And so the height of the shell, which is given by the length of the rectangle, is 2 times the x coordinate, right? So if I stop at y and find the positive x coordinate, all I need to do is double that, and I can get the height. So what I need to do to help me out with that, this is a delta y, a width means I have to integrate with respect to y, and I need to write my integral in terms of y. So I got to take this function they gave me, and I got to get x in terms of y. So y equals 1 minus x squared over 16. I'm going to do some algebra. I'm going to multiply both sides by 16 just to clear denominators, to clear fractions. So I get 16y equals 16 minus x squared. And that means that x squared is equal to 16 minus 16y. I'm going to go ahead and factor out a 16 here. So 1 minus y, there's my x squared. And now if I take the square root on both sides, I could split up a radical over the product, right? So that factor of 16 in there can come out as a 4. And my positive x coordinate is given by positive 4 times the radical 1 minus y. And that means that the height of the shell, which is twice the x coordinate, is 8 times the square root 1 minus y. So for shells, the volume of a sample shell is 2 pi r h times thickness, and that is 2 pi times the radius, that was equal to y. The height, that's this expression that we just found, 8 times this square root. The thickness is delta y. So we got 16 pi y times the square root of 1 minus y delta y. That's our delta v. The limits of this integral, they're going to be y limits. So I imagine sliding this green rectangle up and down through the region. The lowest value is y equals 0. The highest value is going to be y equals 1. So the volume is equal to 16 pi times the integral of y times the square root of 1 minus y dy from 0 to 1. Now this integral, let's just discuss how we could do it. It is possible to do it. This can be done with a substitution of u equals square root of 1 minus y. A little bit cumbersome, but can be done. If that's the case, right, if u is equal to 1 minus y, then u squared, sorry, if u is equal to the square root of 1 minus y, then u squared is 1 minus y. And that means that y is equal to 1 minus u squared. And dy is equal to minus 2u du. And you could make that substitution, right? It would end up looking like the integral 1 minus u squared times u times negative 2u du. And then you could integrate that, right? And you'd have to find your u limits here. So it's possible to do, but you could see that it gives you maybe a slightly more cumbersome integral to do. That's not uncommon, right? That when you're trying to find the volume of a solid of revolution, that one technique will lead to maybe a simpler integral than another one. And occasionally, one technique will lead to an integral you know how to do, and the other one will lead to one that you don't know how to do. So it is valuable to have, both of these techniques available to us. Now, we're not going to actually evaluate these integrals. But the volume, if you want to work it out, if you actually do the evaluate these integrals, and both of them, right, have to lead to the same, both of them will lead to the same result, right? The solid hasn't changed. The solid has a volume, right? So if we got different results from these two integrals, that would be bad news. That would mean something we did was incorrect. But this volume ends up being 64 pi over 15. So if you want to try it out, that's what you should get.